We do have, what, 2 people? Yeah, I think we have 2 people absent right now. So, oh, I'm live. Hey, I'm live. Hey. Okay, cool. So, I want to run an experiment to start this. I want to set up this experiment, and then we'll talk about the results. Then that will lead us into the guided notes that I have for you today. And then after said notes, which, again, that's going to be a little bit lengthy with the notes, but, like I said, you won't have to write down too much. And then afterwards, I do have a video queued up that I'd like to get to, but I don't know exactly how much of the video we'll get through. Whatever we don't get through, I'll post the link to it in the Google Classroom. I don't know if I did that yesterday. Whatever. I'll post it today if need be, and then we'll kind of go from there. I am planning on assigning you guys something out of the textbook that would not be due until sometime mid next week, like I did last time. If you do have any questions about that, of course, tomorrow is already Friday. Seriously, has this week been flying by? I'm just saying, just my opinion. I don't know. But tomorrow's already Friday. We're going to have that virtual Friday. People are just going to hang out and do things. Whatever. Okay, time for the experiment. In a moment, I'm going to give each of you a strip of paper. And on that strip of paper, you will have a string of letters. You all have the same string of letters. Your job, when you get that strip of paper, is to memorize as best you can the order of the letters from beginning to end, whatever. And I will give you roughly about a minute, maybe a minute 15 to get that done. Then I will say, put the slip of paper down. You put the slip of paper underneath your desk. When you've put the slip of paper underneath your desk, you will have an additional minute or so to write down on the note card as many of the letters as you can remember in order. Afterwards, you're going to score yourself. Now, the score will depend on the number of letters that you got right up to the time you messed up. So, for example, if the letters were supposed to be A, B, C, D, E, and you wrote down A, B, C, Q, E, and you messed up right there, you only get 3 points because you only get the number of points up to the time you screwed up, and then no more points. So that's the way that's going to work. We're going to compile our scores, and we're going to see where this kind of goes. All right, so I have 6 strips of paper right here. They have been handily mixed up for whatever reason that is. And I'm going to pass these out to you. So let's see how this goes. Keep them face down. Just for a moment, keep them face down. Keep them face down. Down. I can actually separate paper. Okay. Good. Now remember, you're not writing anything right now. You're just going to spend the next minute and change memorizing. Ready, set, go. For those of you in the chat, you will find out soon enough why this experiment is taking place the way it is. And I will show you once I show them. All right, put the strip paper underneath the desk. You have 1 minute to write down as much as you can remember. Go. right, time's up. Pencils in. Okay, now take the strip back out. Honor system. You got to score yourself. For each letter that you got correct, for each letter that you got correct in order, you get a point. But the moment that you messed up, no more points. Write your score large on the card at the bottom or where in the middle, wherever, so we can all see. So I can see it at least. I'm sorry. Okay, they're still scoring themselves. All right, so you got 21. You got 12. You got 19. Okay. You got 9. Right? And you got 30. And you got 18. Okay. Huh. Interesting results. Let me see what this total is. What is this total? This becomes what? 30, 49. And this becomes, what is that? 60? Yeah. Okay. Results are interesting. Results are interesting. I separated the scores for a reason. Now, your scores still ended up having a total that was in the direction that I thought it would be. But I think that you get the 12. You messed. You know you messed up because you actually had the easier letters. Did you know that? Ooh. You know why they're easier? You got 30. How are they easier? They're separated. Nope. All of them are separated by a little bit. Watch this. I can't see it. Hold on. You guys each had 2 different strips of paper. Some of you had the top strip. Some of you had the bottom strip. They all had dashes. But the reason why the top strip was considerably easier was because where the dashes were being placed made recognizable, not acronyms, what are they called? Abbreviations? Whatever. No, they're acronyms, right? Yeah. And on the bottom, it's like, what the heck am I supposed to be memorizing here? Ugh. On average, the people who have the ones that start out JFK score considerably higher on average. Obviously, there's certain exceptions to that rule. On average, people tend to mess up the bottom one a bit more because it's just a tad bit more difficult to memorize. It's pretty crazy, and it happens every time. Every time I've done this, the people who have had the JFK one have had a higher average or total compared to those who had the other one. It's just the way it is. Now, what I've done by giving you different strips of paper is what we call a manipulation. Again? Yeah. A little bit of a typo, but that's okay. But here's the thing. You didn't know that until now. It did not affect the results of the experiment. FBI, USA, and what's supposed to be SAT? Yeah, so they missed an A there. That's okay. It's perfectly fine. I didn't type this. But the thing is, what I've done is I had a manipulation. Now, again, I did say you had the exact same list of letters. Okay, there's a typo. I throw a brick at your head. I don't know. Anyway, everything else was the same, though. Same conditions, same amount of time, same blue note card, same scoring system. Everything was kept exactly the same. And the only difference between your 2 treatments was that manipulation of where the dash was being placed. Typically, with an experiment, there is a random assignment. I randomly assigned you the strips of paper by mixing them in my hand and then just giving them to you in the order that I walked up and down the desks. Then there is the actual experiment, the treatment, which you did under the similar conditions. Then there are results, which were your scores, which was the response variable in this case. And then there is a comparison, which is the comparison what you see on the board. That's typically what is done in regards to experiments. I mentioned drug trials. For example, if I have a new pill that could potentially cure all headaches, and I get 30 people who are headache prone, and let's say they're put into a condition which induces some kind of a headache, I don't know. And then I split them up randomly, 15 and 15. And the 15 over here, I give them the real pill that I believe will cure their headache. And over here, I give them a fake pill, something called a placebo, typically like a sugar pill, that they think they're getting the real treatment, when in reality, they're not. Because I want to see, does the headache pill actually work? Or is it the conditions where people kind of psychologically think they're getting better, and thus they are getting better? Because sometimes that does happen. Do you guys know what it's called when a placebo potentially works just as well as the real treatment? Ooh. It's like psychologically, people, they're doing the treatment and they think they might be getting better, and then their results compare pretty equally to the other one. It's called the placebo effect. Yeah. It happens a lot. It's pretty crazy. In the realm of experiments, it is very important that you induce some kind of randomness. You have to have some kind of a randomness. When it comes to the notes that we're about to take in a little bit, I'm going to talk about how randomness could come into play. It's going to seem very silly. With you guys, it's like you're human beings. Of course, you have to be randomized. But I'm going to show you something with a washing machine in a little bit and T-shirts. And imagine 30 identical T-shirts. It may not make much sense to be like, well, why would you randomize 30 identical T-shirts? I don't know. They're identical T-shirts. I really don't know what their journey has been. Maybe some of them were manufactured in this part of the country. Maybe the others were manufactured in this part of the country. Maybe these shirts were just manufactured last week. Maybe these shirts were manufactured 2 years ago. I don't know. And since I don't know, my best option is to randomize, because that eliminates any possibility, or not any possibility, but it reduces the chances that maybe all the brand new shirts would go into this treatment and all the old shirts would go into this treatment, and then my results are completely screwed up. All right, what do I want to do with those? Nah, you keep them. Souvenirs. Have fun with those. Put them up on your fridge. Okay, I don't care. Anyway, what I want to give to you next, I want to give to you those guided notes. Now, for those of you in the, what is today, Thursday? Yeah, for those of you in the chat, I think I put them into the Google Classroom, did I? Let me double check that. Pretty sure I did. Yes, on September 30th on the Google Classroom live stream, it says guided notes for chapter 12. Okay, so they have that. And now you will have this. Now, a lot of this information, as I said, was taken directly from the textbook. There are a lot of textbook definitions in here that I would have you write down normally. I would have you write them down normally. I would have you kind of like, just jot random things down. I have amended some things on my paper here that I'm going to have you amend on yours as well. Not really cross out, but kind of add if need be. Let me bring up, I should have brought it up over here. I would really love like a wireless kind of microphone or something like that. It would be amazing if I could. Where is it? AP stats. 30th. Boom. Huzzah. So these are what the notes obviously look like for those in the live chat. You should be seeing that. But let's talk about some of this. First of all, experiment. An experiment is a procedure for investigating the effect of an experimental condition on a response variable. I want you to write down this little extra note. An experiment has a manipulation of some sort. An experiment has a manipulation of some sort. In order for it to be deemed an experiment, it has to have something like that. Now, that manipulation is often referred to as a treatment, which they do have defined a little bit later on. But I just want to make sure you know that. In the chapter 12, they talk a bit about experiments and they talk a bit about observational studies. Now, observational studies, it already has it in the word, observation. You are literally just seeing what happens without inserting yourself into the situation. That's an observational study. But if it is an experiment, then you are inserting yourself in some way in order to manipulate the situation. Everything else has to stay the same, and then there has to be some kind of manipulation, which could be more than one thing. We're going to talk about that. Experimental units, individuals on whom the experiment is being performed. You are my experimental units. However, it is not PC to refer to you as experimental units. We typically refer to you as what's in the parentheses there, usually called subjects or participants. Under the word subjects or participants, write the word humans, because if you're a human being in the experiment, then you are a subject or a participant, not an experimental unit. Experimental units are typically, that kind of terminology is typically referred to for inanimate objects and animals. A factor. Now, factors, treatments, that kind of thing, it's going to make a little more sense when I draw my picture on the board in a little bit, which you're going to copy. But a factor is a variable whose levels are controlled by the experimenter. The factor in the experiment that I just did with you was the list of letters or the strip of paper with the letters. How many levels did I have in my experiment? How many levels did I have in that factor? Just two. In my opinion, the easy letters and the hard letters. I'm going to draw a picture for it in a little bit. You'll see. Extraneous factor. A variable that is not of interest in the current study, but is thought to affect the response variable. Now, I want to be very clear about something. Put a note next to extraneous factor. It is typically a good idea to avoid this. Typically a good idea to avoid this. A variable that is not of interest in the current study, but is thought to affect the response variable. Here's an example. Some high school students would argue me on this one. But what if, while you were memorizing the letters, I allowed randomly whichever ones of you wanted to listen to music? Because some people say, Mr. Markey, I study better when I listen to music. Okay. That doesn't really interest me in terms of this thing. The interest in my experiment was figuring out the memorization of the letters and whether it was easier or harder depending on where the dashes were. Music has nothing to do with it, but that could affect my results. I would have to remove that from the equation, listening to music or any other type of distraction, in order to not let it affect my results. And a treatment, I'm going to go to confounding much later, but a treatment is the process, intervention, or other controlled circumstance applied to a randomly assigned experimental unit. Treatments are of different levels of a single factor or made up of a combination of factors of two or more factors. Now, that's going to make a little more sense once I draw my picture on the board. First, the washing machine thing. You'll see. But for my experiment, I had two treatments. I just had two treatments. That's all I had. Here's what I need you to do. I'm going to draw something right now, and I'm going to need you to copy it. Now, you can put it directly on these guided notes on like the back page or something like that. I did do front and back. The back page does have a little space there, or you could put it on a separate sheet of paper. That's up to you. That's completely up to you. Your notes, your future. What we got here? Boom. I'm going to zoom out. So let me talk about those t-shirts. Here we go. So let's say in my experiment, I just started off with 30 t-shirts. I went to the store and I purchased 30 identical t-shirts. Then with these t-shirts, I what we call randomly allocate. It's just literally randomizing them into groups of 15 and 15. There's a group of 15. There's a group of 15, and they are randomly allocated into two groups of 15. But then I go a little bit further, and perhaps I randomly allocate them again into groups of 5. is a tree diagram. You guys have seen tree diagrams for a bunch of different things in your careers in math. You're going to see tree diagrams much later on when we cover the chapter on probability as well. Now, here's my goal for this experiment. I want to determine which washing machine, the brand name washing machine. What's a brand name of washing machine? LG? I don't know. I've heard of Maytag, though. LG I have heard of, but I didn't know they made washing machines, do they? All right. Whatever. Brand name. So there's the brand name of washing machine, but then I do know they have this. If you go to Home Depot or Lowe's, they have generic brands of washing machines that are like at least $200 cheaper. So you have brand name versus generic name. And I want to find out, okay, is the brand name really that much better? Which one performs better in washing shirts? But the thing is, the reason why I've split it up like this is because I have this idea in my head that the level of dirt could affect how well the washing machine performs. If it's like heavy dirt or light dirt or something like that, I don't know. So I've designated for myself 3 levels of dirt: high, medium, and low. And that is exactly what I'm going to do these t-shirts. These 5 t-shirts in each category, we're going to, now here we go. We're going to give them a certain level of dirt. We're going to give them high dirt, medium dirt, or low dirt. High dirt, medium dirt, and low dirt. There is my dirt. Now, dirt is a factor. Dirt is a factor. If you go back to the definition on the paper, a variable whose levels are controlled by the experimenter. I'm controlling the levels of the dirt. I'm creating these different levels of dirt that each t-shirt is going to experience, however which way I decide that would be. Then, perhaps, and again, this is not the only way to do this. There's 100 different ways to do this. In fact, I'm going to ask you your opinion on how I could improve this experiment in a little bit. But then I could take each of those shirts and we can run them through the brand name washing machine. The brand name washing machine. Now, keep in mind, I'm going to run them through separately. I have to run them through separately. Because if I run through a low dirt shirt with a high dirt shirt, that could definitely mess up my results. So I'm going to run them through separately. Same thing for the generic brand. I'm going to run them through separately for the generic brand. What would be ideal? What would be ideal, which I don't think that is really cost effective, is if I got 6 different washing machines, 3 brand names and 3 generic. I don't have enough money to do that, clearly, if I'm like a small-time experimenter. But if I'm working for the company that makes these washing machines, perhaps I would have the resources to do something like that, where you could get 6 different washing machines in order for cross-contamination not to happen. It seems very silly to do something like that. It's just a washing machine, I know. But as an experimenter, you don't want to take many chances. So then, after the brand name thing goes through, we're going to compare those results. After the generic shirts go through, we're going to compare those results. And then ultimately, we're going to compare all results together. It's a giant comparison at the end. This is a very basic type of tree diagram which expresses how I'm going to run this experiment. Now, question. How many treatments did I impose on this experiment? How many treatments? I'm being very specific with my words, by the way. Being very specific with my words. I'm using the word treatment. Ooh. Take a guess. Not 3. Yeah. I don't know if you were going to clap. There's 6. There's 6 treatments. I'm being very specific with my words here. There are 6 treatments. Basically, if you are a t-shirt, I know that's very hard to think of, but if you are a t-shirt at the beginning of this process, you have the possibility of going through one of 6 different treatments, unique treatments in this experiment. So there are 6 treatments. How many factors are there? Just factors. How many? There are not 3. There are not 3. Not also 6. Yeah? Nope. 5? No. 2. There are just 2. The 2 factors in question are dirt and washing machine. Those are the 2 factors. Those are the 2 variables, so to speak. If you read factor, a variable whose levels are controlled by the experiment. There are 2 factors to this experiment. Dirt, washing machine. How many levels are there to the dirt? 3. How many levels are there to the washing machine? 2. By the way, 3 times 2. That's how many treatments you got. That's how this thing kind of works. Basically, you look at the levels per factor and multiply the number of levels together, and that's how many treatments you typically get. Or you can just literally, as I saw several of you doing, just count them. There are 6 possible routes that a t-shirt could go in the journey of this experiment. Before I get to the rest of the notes, because I want to ask you this question. Do you know a way right now where you could improve my experiment? There's always a way to improve something. But there's a very basic way that I left off on purpose because I wanted you to figure it out. Ask it. Say it. Now, we're going to get to this definition a little bit later. But have you ever heard of the concept of a control group? Okay. What would a control group look like for this experiment? Not that it was never washed. That was never dirty. Yes. You take a shirt that has no dirt, that was never dirty, and you create a 4th category here for no dirt and no dirt, and that would be your control group. Because the shirt's still going through the experiment. Because remember, we're trying to figure out the effectiveness of these washing machines. That's the whole goal of the experiment. And you have to have a base of comparison. That's going to be in the notes a little bit later, the idea of a control group. But it's a base of comparison. So it's like, okay, here's a shirt that went through, washed through the washing machine. You don't want to do it with no wash, because if you do it with no wash, then this shirt has no connection to the washing machine whatsoever. It's a very technical thing, and it seems like very tedious. But this is how experiments are typically put together. Confounding variable. A confounding variable is associated in a non-causal way with a factor and affects the response, usually found in experiments. Because of the confounding, we find that we can't tell whether any effect we see was caused by our factor or by the confounding variable, or even both working together. Now, I won't read the paragraph that they have there underneath of it, but I'm going to tell you the story of it. There was a professor who decided that he was going to have an experiment to test out 2 different types of teaching styles. So he decided, okay, I'm teaching this class, the same class in the fall and in the spring semester of college. I'll teach the class in the fall with teaching style A. And then in the spring, I'll teach a different group of kids, but the same class, I'll teach them with learning style B. And the idea is like, okay, you have maybe like 100 students randomly. They break up into 50-50. I don't know how. And then like 50 take the class in the fall, 50 take the class in the spring. And then they get the teaching style. Maybe they don't get both teaching styles. I don't know. There's a bunch of different ways you can go about doing that. But the problem is there's a confounding variable. In the end of the semester, he would have the students surveyed to determine how they felt about the teaching style, how they felt about how well they did in the class, and also be able to compare their grades as well. but there was a confounding variable. What kind of weather usually ends up happening by the end of fall? Cold and dark and gloomy. What about the end of spring? Sunny, sun shining, freshmen coming out on the quad playing their guitars. That's what happens in college. It's dumb. See, the thing is, would you say that weather could affect your mood and how well you may have performed in that class? Heck yeah, it's a possibility. You might say to yourself, well, I don't get affected by the weather. I understand that, but other people do. And if they're randomly being allocated, then the results are going to be confounded by the type of weather. Whereas on average, you might have lower results in the fall and higher results in the spring, and it may not be because of the teaching method, it may be because of the weather. And since, going back to confounding variable, because of the confounding variable, we find that we can't tell whether any effect we see was caused by our factor or by the confounding variable, or even both working together. There is a term, remember I told you about the storks in the village and stuff like that? In that wasn't confounding. That was actually something that they call a lurking variable. A lurking variable is typically done with samples of that sort, where it's not an experiment. You're just kind of collecting data. More observational in that sense. That's a lurking variable. Whereas in an experiment where there is some level of manipulation, it's a confounding variable. At the bottom now, I'm looking at direct control, holding extraneous factors constant so that their effects are not confounded with those of the experimental conditions. I did that for you in the experiment with the letters. I tried to hold everything the same. Everyone had the same strip of paper, same type of paper, same note card, same amount of time, same amount of quietness in the room. Everybody had the same experience. That was my level of control over this thing. Next page. They use the word blocking. Now, let's go back to Boston cream pie. What's it called when I go to a Boston cream pie and I separate it into its like individual components and then sample a little bit from each? Cluster is a slice, where you slice it and then you get that slice has everything in it. Stratified. The reason why, if you separate it into the chocolate and the cream and the Boston, if you separate it into those pieces, those are called the strata. And then that's stratified sampling. Stratified sampling is when you, like I said, you take maybe the Barnegat High School population and you split them up into freshman, sophomore, junior, senior into their individual strata, and then you sample a little bit from each. In an experiment, that's called blocking. When groups of experimental units are similar, they have common factors, it is a good idea to gather them together into blocks. By blocking, we isolate the variability attributable to the differences between the blocks. Now, let me give you an example. You're all in high school. Good job. Let's say that I had a lot more kids in here. There's a lot more kids where I had maybe a group of middle schoolers and I had a group of elementary school kids, all learning AP Stat. Good for them. If I was going to run that experiment with the letters, it would be a great idea if I did blocking by level of school. Because I would argue that a high school student has a better chance of memorizing a string of letters in a short amount of time than an 8-year-old kid. That would be my argument. So perhaps it would be a good idea to block by age. I don't know. Just is. Silly example I was just thinking of, but I don't know how this would apply to you guys because you might fall into the same category. If I wanted to do an experiment taste test with like generic versus brand name chicken fingers, perhaps it would be a good idea to block by age as well. Although I don't know how many of you still go into a restaurant and just get the chicken fingers. Okay, that's fine. Get something else. Come on. Anyway, it's totally fine. I'm just, oh gosh. Anyway, back to this. So that's blocking. Again, there's a lot of different examples. You can even see for the example that they gave, the levels of age are called blocks. It's a good idea to block if you can, but it depends on the situation. It depends on the context of the situation. Sometimes blocking, You just can't come up with a reason for it. And if you can't come up with a reason for blocking, then don't worry about it. Let it go. But in that example with the letters and the age groups, yeah, it might be a good idea if I blocked by age in that case, or by level of school. Okay. If you should, then yeah, absolutely go for it. Placebo. We talked about placebos before. A treatment known to have no effect, administered so that all groups experience the same conditions. Only by comparing with a placebo can we be sure that the observed effect of the treatment is not due simply to the placebo effect. I mentioned the placebo effect earlier, the idea of the sugar pill, the placebo pill, helping somebody get better with some headache issue compared to somebody who took the real pill. The placebo effect, the tendency of many human subjects to show a response even when administered a placebo. Question: is it possible in my experiment for the placebo effect to happen? For this one right here that I'm pointing to, is it possible for it to happen? No. They're inanimate objects. Yeah, they're inanimate objects. There's no way. Oh, the shirt felt it was cleaner. No, it's a t-shirt. The washing machine felt it did a better job. No. Control group. The experimental units assigned to a baseline treatment level. Typically either the default treatment, no treatment, or a placebo effect. Now, if you wanted to make, again, there's 100 different ways to do this experiment. There's 100 different ways to do it. You want to make it better? Create that control group. Have a set of t-shirts, go through the washing machine with no dirt. Better yet, add a fifth one that doesn't have any dirt and doesn't have any washing machine. I don't know. Maybe that could be helpful for comparison. You never know. You want to make sure all your bases are covered. Could be a good idea. Blinding. You were blinded. You, as the subject, was blinded to my experiment. My experiment was a single blind study. It was a single blind study because you were blinded. In a double blind, we'll talk about that in a minute. Sometimes it's a good idea for you to be blinded because imagine if you knew that some of you got the JFK strip and some of you got the JF strip. If you knew, some of you might be kind of annoyed. Crap, I got the harder one. And that could affect my results. Perhaps people who got the JF strip would be trying harder as a result, or people who got the JFK strip would be not trying as hard because maybe they thought, oh, it's easier, So I had to blind you to that fact. Blinding any individual associated with an experiment who is not aware of how the subjects have been allocated to treatment groups. It is, now you can write this extra little note here, necessary if knowing the treatment would affect the results. Being blinded is necessary if knowing the treatment would affect the results. You have to be able to control that. Now, a double-blind study, it makes no sense for the experimenter to be blinded as well. The experimenter has to know what the results are going to be. It'd be very important. But you could blind on the other end. By the way, I'm still on blinding, by the way. I'm not to double blind just yet. But you could blind on the other end of the experiment by having the person who is doing the evaluating be blinded. You can have the person who is doing the evaluating be blinded. Now, as the experimenter, I know everything that's going on because I designed it. You come in as my subjects, you're blinded, you perform the experiment, and then somebody does an evaluation of that, and that person does not know what treatment you got. That person does not know what treatment you got. That person is also blinded, or could be singularly blinded, it doesn't matter. But me as the experimenter, I can see it all. You could do double blind, as it says right there, when every individual who can either influence the results or evaluate the results is blinded. That's important. Again, as the person organizing this whole thing together, I need to know what the heck's going on, so perhaps I would not be doing the evaluating. There is one great example, which I don't think we're going to get to, and definitely not today. We'll probably have to get to like another time, but it was called dolphin therapy. I mentioned dolphin therapy to you guys? No? Okay. Very briefly, dolphin therapy. 30 people were brought down to some Caribbean resort, and they were split randomly into two groups, 15 and 15. Now, these 30 people in the past had experienced some level of depression. Before they went on the vacation, they were evaluated by a psychologist who did not know what group they would be put into. So the 30 people went down to vacation, split 15 and 15. 15 of them just had the regular vacation. The other 15 had the regular vacation, and they got to swim with dolphins. Yeah. Then when the vacation was all said and done, the psychologist evaluated them again, not knowing whether they had the dolphin therapy or not. Now, in this case, the people going down on vacation, they are not blinded. They know exactly what treatment they're getting. They know whether or not they're going to swim with dolphins or not. But the psychologist does not know. And as a result, is able to give an objective, I can't even talk today, objective point of view in terms of whether or not their depression improved or worsened. I mean, come on, you're going on vacation. But dolphins are evil. Anyway, back to this. Principles of experimental design. I'm on the next page. These are important. I would probably put a star next to this if I were doing my own notes. The principles of experimental design, you have to randomize. There has to be some kind of randomization. You have to. Think about that pot of soup. If I'm going to experiment whether or not adding certain spices is going to affect the taste of that soup, I'm going to experiment with this soup and then maybe this soup with other spices. I don't know. But then you need to mix that whole thing together. Because if you do not randomize, you are going to get a pretty not tasty soup. Subjects are to treatments to even out the effects we cannot control and or to ensure the experiment does not systematically favor one experimental condition over another. Control. You have to have control over things. You have to have control in the sense of creating similar circumstances for everybody going through the experiment or everything going through the experiment. You have to maintain control. Replicate. Now, replicate could mean one of two things. Replication could mean one of two things. Replication could be, hey, look, I had 5 shirts go through the high dirt level on the generic machine. I replicated that 5 times. That's replication. I had 5 shirts going through each of these treatments. That's replication. Or somewhere in Florida, someone else decides to run this exact same experiment to see if they can replicate my results. That is also replication.
So if you wanted to have a control group for this sort of experiment,
Sure.
would we just get one from the lower side, or would we just add one to the level?
Oh, good call. I would probably make this 40 shirts then. 40 shirts, 20 and 20, and then have another 5 go through there. It's not required. It is not required that these numbers match. It is not. It is a good idea to replicate, of course. Like if this was like 16 and 14, okay. That's fine. Because you did have 16 go this way and 14 go this way. That seemingly should be enough. It's just that these numbers would be uneven, but them's the breaks. Blocking. Now I want to put, again, a little note next to blocking. Not required, but a good idea if you can. Blocking reduces the effect of identifiable attributes of the subjects that cannot be controlled. If it makes sense to break up the subjects or experimental units by some attribute similar to stratified sampling, then yes, go ahead and do blocking. They say the best experiments are usually a randomized, comparative, double-blind, and placebo-controlled. Now, there's a list of things there before proceeding with an experiment. I want you to write next to number 8. Right next to number 8, absolutely necessary. Absolutely necessary. How does the design incorporate random assignment of subjects to treatments? Randomization doesn't always have to happen exactly the same way, but it has to be incorporated into your experiment. Now, the next few pages are going over an example. You can read that on your own. The next few pages are talking about tomato plants being randomly assigned and put into groups. And you can see even right here, the tree diagram that they did, similar to mine, but obviously in a different style. And you can see the comparison of things at the end. They give you several different examples. Several different examples. And then what can go wrong? Because, of course, something will ultimately go wrong. If you're dealing with human beings or if you're dealing with inanimate objects that could break down over time, of course, something could go wrong. I'm going to ask and expect that you guys review these notes on your own. I am going to be assigning something out of the textbook before the end of today that we do the middle of next week, which will be based on the stuff in chapter 12. Of course, there's also on Google Classroom, there is that assignment for the next part of your project. Wait, no, the first part of your project, right? Yeah, I think I'm going to double check that. I believe it said part 1. Good, I'm sorry. I'm mixing you guys up with ProbStat. ProbStat's moving at a different pace than you because they're not covering as much information. ProbStat is like the trial version of AP Stat, the one you don't pay for. You know what I'm talking about? Okay, cool. But yeah, they're on part 2. You guys are on part 1. So you guys are fine. But that's due tomorrow by 2 o'clock. All right. Yay. All right. Now, at the time that we have left, like I said, we may not be able to finish the video that I have queued up, but I want to watch a good chunk of it. Now, a couple of things before we start it. Number one, I will throw on the link onto Google Classroom so you can finish it if you don't get the chance, especially for those who are absent today. Furthermore, I can hope that at this point in your high school careers, we can be mature about foul language or something like that. No, get the heck out. Anyway, yeah, because there is a little foul language in it, but that's not the purpose of it. There is a bit of off-colored jokes, but again, not the purpose of it. The purpose of it is the substance to which the man is talking about. Some of you may be familiar with John Oliver. This video was from like 4 or 5 years ago, and it was in regards to experiments and observational studies. Now, he doesn't call them that. He calls them scientific studies, but it's the same thing. The general concept of either observing data, collecting the data, analyzing it, and coming to a conclusion, or conducting an experiment, comparing the results and coming to a conclusion. But in today's day and age, there's a bit of an issue. There is a bit of an issue with experiments. Let's see what happens here.
Science, the thing we love and respect so much, we only allow scientists to be portrayed by the likes of Arnold Schwarzenegger, Nicolas Cage, and Al Pacino. That is how much we respect them and the complexity of the work they do. Science is constantly producing new studies, as you would know if you've ever watched TV.
A new study shows how sugar might fuel the growth of cancer. A new study shows late-night snacking could damage the part of your brain that creates and stores memories.
A new study finds pizza is the most addictive food in America.
The new study suggests hugging your dog is bad for your dog.
A new study showing that drinking a glass of red wine is just as good as spending an hour at the gym.
All right, a couple things. First of all, a new study shows, a new study shows, a new study shows. It suggests, evidence suggests, that's the fluffy language that we've been using, which is exactly what I've been teaching you. This is exactly the point of this. But think about that for a second. A new study shows that drinking a glass of red wine is equivalent to an hour at the gym. Wow. Now, it suggests it. They're not taking a definitive stance on it. They're suggesting it. But what happens when you say something like that on the local news? Yeah. They think it is, yeah. Back in the 90s, you don't know this because you weren't alive. Back in the 90s, every other year, eggs were good for you, then bad for you, then good for you, then bad for you. Then all of a sudden, no, it's trans fat. something else. No, now here's a new superfood, acai berries. No, you need to be eating dark chocolate. No, you need to be doing this. No, you need to be doing that. Every single year there's something different because there's a stupid new study that comes out that they only do one experiment with and nobody ever replicates it. Anyway.
What? That last one doesn't even sound like science. It's more like something your sassy aunt would wear on a t-shirt. And when studies aren't blanketing TV, they're all over your Facebook feed with alerts like study finds liberals are better than conservatives at smizing, your cat might be thinking about killing you, and scientific study shows that bears engage in fellatio. And by the way, I'm not interested. Let me know when bears start engaging in some mutually pleasurable 69ing. Hashtag fair pleasure, hashtag feminism. Time.com once even ran the headline, scientists say smelling farts might prevent cancer, which I would say was the most unfortunate thing Time ever published. But then this is a magazine that once did a cover story on those Asian American whiz kids. The point is, there are now so many studies being thrown around, they can seem to contradict one another. In just the last few months, we've seen studies about coffee that claim it may reverse the effects of liver damage, help prevent colon cancer, decrease the risk of endometrial cancer, and increase the risk of miscarriage. Coffee today is like God in the Old Testament. It will either save you or kill you, depending on how much you believe in its magic powers. And after a certain point, all that ridiculous information can make you wonder, is science bullshit? To which the answer is clearly no, but there is a lot of bullshit currently masquerading as science. So tonight, we thought we'd talk about a few of the reasons why. And first, not all scientific studies are equal. Some may appear in less than legitimate scientific journals, and others may be subtly biased because of scientists feeling pressured to come up with eye-catching positive results.
My success as a scientist depends on me publishing my findings, and I need to publish as frequently as possible in the most prestigious outlets that I can.
Now, that's true. Scientists are under constant pressure to publish with tenure and funding on the line. And to get published, it helps to have results that seem new and striking, because scientists know nobody is publishing a study that says nothing up with acai berries. And to get those results, there are all sorts of ways that, consciously or not, you can tweak your study. You could alter how long it lasts, or make your random sample too small to be reliable, or engage in something that scientists call p-hacking. That's p-hacking with a hyphen, not to be confused with facking, which, as I think everyone knows, is a euphemism for fucking the Philly fanatic. Now, p-hacking is very complicated, but it basically means collecting lots of variables and then playing with your data until you find something that counts as statistically significant, but is probably meaningless. For example, I mean, he's going to go over a bunch, but for example, I collected data showing that, well, the number of storks increased, and then afterwards, the number of babies increased. Clearly, that's statistically significant. Website 538 surveyed 54 people and collected over 1,000 variables, and through p-hacking the results, was able to find statistically significant correlations between eating cabbage and having an innie belly button, drinking iced tea and believing Crash didn't deserve to win Best Picture, and eating raw tomatoes and Judaism. And the only thing tomatoes have in common with Judaism is that neither of them really feel quite at home in the upper Midwest. But you don't even need to engage in these kinds of manipulations to get results that don't hold up. Even the best designed studies can get flukish results. And the best process that science has to guard against that is the replication study, where other scientists redo your study and see if they get similar results. Unfortunately, that happens way less than it should.
Replication studies that are so really funded and they're so underappreciated, they never get published. No one wants to do them. There's no reward system there in place that enables it to happen. So you just have all of these exploratory studies out there that are taken as fact, that this is a scientific fact that's never actually been confirmed.
Exactly. There is no reward for being the second person to discover something in science. There's no Nobel Prize for fact-checking. And incidentally, there's no Nobel Prize for fact-checking is a motivational poster in Brian Williams' MSNBC dressing room. And for all those reasons, scientists themselves know not to attach too much significance to individual studies until they're placed in the much larger context of all the work taking place in that field. But too often, a small study with nuanced tentative findings gets blown out of all proportion when it's presented to us, the lay public. Sometimes that happens when a scientific body puts out a press release summarising the study for a wider audience. For instance, earlier this year, a medical society hosted a conference at which a paper was presented comparing the effects of high and low flavanol chocolate during pregnancy. If that sounds narrow and technical, it was supposed to be. There wasn't even a control group of women who didn't eat chocolate, and the study found no difference in preeclampsia or high blood pressure between women who ate the two chocolates. So there is no way a study that boring can make it to television, right? Well, wait. Because that medical society issued a press release with the much sexier but pretty misleading title, The Benefits of Chocolate During Pregnancy. And because most TV producers just read press releases, this happens.
Turns out if you're pregnant, eating 30 grams a day of chocolate, that's about 2/3 of a chocolate bar, not the whole chocolate bar, could improve blood flow to the placenta and benefit the growth and development of your baby, especially in women at risk for preeclampsia or high blood pressure in pregnancy.
Except that's not what the study said. It's like a game of telephone. The substance gets distorted at every step. And I can only imagine how someone who watched that segment must have described it the next day. Oh, the news said our baby is made of chocolate and it's okay if I eat it, but only 2/3. And it is not like the media needs help blowing things out of proportion. Remember that Time story about farts and cancer? It turns out the study never mentioned either of those things. It just pointed out that certain sulfide compounds are useful pharmacological tools to study mitochondrial dysfunction. And while that Time story was later heavily corrected, the scientists told us that we still get phone calls and emails from strange radio and TV shows wanting us to talk about farts, which is clearly a waste of their time. They're doing valuable work. They shouldn't be wasting their time fielding calls from drive time DJs, Gasman and The Beef. And there is no doubt some of this is on us, the viewing audience. We like fun, poppy science that we can share like gossip, and TV news producers know it. That is why you constantly hear stuff like this.
Men, listen up. A brand new study says a woman is more open to romance when they are full opposed to being hungry.
Okay. First of all, no shit. Anyone is more open to anything when they aren't hungry. But you should know that study involved only 20 women. And you cannot presume that 20 women can speak for all women. This is science, not the United States Senate. And then there was this eye-catching report from just last year.
A university in England says drinking champagne every week may help delay dementia and Alzheimer's disease. They say only 1 to 3 glasses a week, not a day, a week, can be effective for your health.
Fantastic news.
No, it isn't. No, because there's a big issue with that study, aside from the fact that if you are celebrating with champagne 3 times a week, your standards for celebration need to be much higher. Champagne is acceptable on New Year's, Valentine's, birthdays, and if and when Henry Kissinger dies, and that's it. That is it. That is the full list. But the bigger issue is that study was performed on rats. And how do you not tell people that? And how do you not also show them photos of the experiments? Oh, you'd think they would have paired it with some cheese, but it appears they went with cocaine. God, that's chic. Those are chic rats. It's not the drugs that make them cool, it's their confidence. But the truth is, while studies performed on rats and mice are undeniably useful, their applicability to humans can be limited. The overwhelming majority of treatments that work on lab mice do not wind up succeeding in humans, which means 2 things. A, we shouldn't rush out to report rodent results. And B, during lab mouse funerals, when they say, at least he didn't die in vain, most of the time they are lying. I know it hurts to hear that, but them's the breaks, mouse. Now, to be fair, it's not always the news media. Sometimes researchers themselves will oversimplify the science. Even TED Talks, which have had some amazing speakers, have also featured some morning show-style science in the past, like Paul Zach's 2011 talk on a hormone produced in the brain called oxytocin, which he even gave a catchy name to.
This little syringe contains the moral molecule. It's so easy to cause people's brains to release oxytocin. I know how to do it. And my favorite way to do it is, in fact, the easiest. Let me show it to you. Come here, give me a hug. There you go. Here's your prescription from Dr. Love. 8 hugs a day. We have found that people who release more oxytocin are happier. And they're happier because they have better relationships of all types. Dr. Love says 8 hugs a day.
First of all, don't call yourself Dr. Love. That's the nickname a tabloid gives a dentist who ejaculated on his sedated patients. And second, there is no way that I would be happier giving 8 hugs a day. I'm English, that is 4 lifetimes worth of hugs. And look, by now, you probably won't be surprised to learn the real science on oxytocin is more complicated than the term moral molecule suggests. Because while it has been found to enhance positive emotions like bonding and trust, researchers have also found that it can enhance negative emotions like envy and bias. So while promising, the science on this is still very much in progress, which probably explains why a recent survey of oxytocin research warned the reports about it influencing a large number of social behaviors should be viewed with healthy skepticism, which is really a long technical way of saying what you probably knew in the first place, which is when a strange man calling himself Dr. Love offers to hug you 8 times a day, say no. And you can see just about all of the problems that I've described, plus one more in a study that made the rounds last year.
The new study claims that driving while dehydrated is just as dangerous as driving drunk. Researchers say drivers who drank just 1 ounce of water per hour made the same number of mistakes on the road as those over the legal limit with alcohol. Doctor, when I heard this, I thought this cannot be true.
Yeah, obviously it couldn't, because it wasn't true. As Britain's National Health Service had already pointed out, that study was riddled with red flags, including that it was based on just 12 men, of whom data was only reported for 11, and it got funding from the European Hydration Institute, a foundation that has received over $7 million from Coca-Cola, a company that just happens to sell rehydration in the form of fizzy brown sugar water, carbonated urine, flat urine, diet urine, and grapefruit-flavoured embalming fluid. And look, just because a study is industry-funded, or its sample size was small, or it was done on mice, doesn't mean it's automatically flawed, but it is something the media reporting on it should probably tell you about. And you may think, well, hold on, where's the harm here? So long as I don't try to fart cancer away or fillet a bear, no one's getting hurt. But I'm not so sure about that. Because think of it this way. This is a chart mapping the results of studies of things like coffee, eggs, and wine. All of them have been linked to raising or lowering your risk of cancer, depending on the study. And everything causes cancer is not the conclusion you want to draw from science. It's the conclusion you should draw from logging onto WebMD, where that is their motto. Because if I were to tell you about each of those studies in isolation, at some point you might reasonably think, well, no one knows anything about what causes cancer. And that is a problem, because that's the sort of thing that enabled tobacco companies for years to insist the science isn't in yet. And if you think I'm exaggerating about the impact that this misreporting can have on our faith in science, look at an example from some of the people most guilty of it. Because the Today Show, which lives for scientific studies, recently concluded one segment like this.
Like a lot of studies that we love around here, there have been a couple, especially related to women, about the benefits, as I get all serious on whole milk. Hey, whole milk, but it's true.
There's a lot of research, though, that says actually having whole milk or having whole fat dairy products actually can help you lose weight.
I think the way to live your life is you find the study that sounds best to you. And you go with that.
No! In science, you don't just get to cherry pick the parts that justify what you were going to do anyway. That's religion. You're thinking of religion. That is what you're thinking of there. And look, this is dangerous. This is really dangerous. If we start thinking that science is a la carte, and that if you don't like one study, don't worry, another will be along soon. That is what leads people to think that man-made climate change isn't real, or that vaccines cause autism, both of which the scientific consensus is pretty clear on. Science.
We're actually out of time. There is more things in the video that are funny. I'm going to post it to Google Classroom. If you want to finish it, you can. That's up to you. But we'll see you next time.